Pretty good. I'll give you that. That's everyone. Are we live? All right. Seems to be doing something. Rid of this. And here we go. Okay. So I guess we can get started. I'm at 21. Oh, I posted it, right. This is 20, yeah. Thanks. So make 22. All right, so let's get started. So last lecture, well, I guess the lecture before last. So last lecture, I posted the remainder of that algorithm for reduction of derivatives. And when we were doing that, you should now have basically all the tools that you needed for that assignment. So I realized the assignment was due today, but you have until tomorrow, basically at 2 o'clock in my office, to hand that in. But is anything, before I go too far, is anyone not clear on anything with that algorithm? Awesome. Okay. So previously, we've discussed the possibility of multi-phase systems. And by multi-phase, I mean, so you have single component, but multiple thermodynamic phases. So say an ice cube in a glass of water, or fog as you're driving along by a lake, right? So you have one material, water, that exists, has several different phases. And I want to understand today, basically, what do I have to think about as I move from one phase into another? And what are the rules? So for example, can I have an ice cube that sits in water? Will it stay there indefinitely? If I have, say, a glass of water in a large room, does it necessarily evaporate? And I want to understand the sort of the rules and different conditions associated with these phase transitions. So there are basic questions which need to be addressed. And although what I'm talking about today is basically going to focus on a single component system, in principle, you can generalize it to multi-component systems. So for example, if one had access to pierogies, you can look at the various phase transitions that take place as you melt the ice around the pierogi and you melt the cheese, and the delicious pierogi aura comes wafting off of your skillet. You can see now why we arrived at pierogies in the classroom. But for the purposes of today, we're going to stick with a single component. So the question fundamentally is, what decides whether a material is a solid, a liquid, or a gas? How does the transition occur? Are all transitions the same? And are multi-phase mixtures stable? And by stable, I mean at equilibrium. Question mark. All right. So let's start with an experiment. And the experiment is going to be the following. So suppose that I have some piston, all right, or a container, where I have 3 rigid walls, and I can change the volume of the container by a piston. Right, so this guy goes in, volume goes down, this guy goes to the opposite direction. And I know that initially the system will start off in some phase, and let's assume that initially it's a liquid, okay? So I have this liquid sitting in a piston, and I'll have enough liquid so that it completely fills the volume. And the system is at some particular P and T. So this is a liquid, this is a piston. So starts off at some pressure and temperature. And let's now pull out the piston. Increasing the volume at constant temperature. Right? So in order to do this, to maintain constant temperature, that means that I need to be able to either give up or extract, or give up heat to or extract heat from the surroundings, which implies that the container is dithermal. Diathermal. Okay. So previously, when I've mentioned phases in passing, without much discussion, I sort of drew a diagram that looks like this. And this is potentially something that you have seen in your other courses. Where I'm plotting pressure as a function of temperature, and these lines denote transitions between phases of material that you've probably heard about. All right, so when you initially, as a child, learn about phases, right, in grade 1, you do different experiments where you take water and you point outside and you say, look, it's wet outside. That's a phase of water. Everyone goes, okay, fantastic. And then on another day you say, it's foggy outside. That's another phase of water. And the kid goes, okay. And then you say, look, there's an ice cube, and then there's another phase. And the kid goes, okay. And you said, and therefore there are 3 phases of matter, solid, liquid, and gas. And all the children go, okay. And then some child puts up their hand and then says, what is snow, right? And the teacher says, look over there, and basically ignores that entire problem, right? And say, as I said before, there are 3 phases of matter, solid, liquid, and gas, right? Okay. So the teacher didn't entirely lie to the children. I mean, don't get me wrong, we all lie to you. But that is a true statement. Solid, liquid, and gas are different phases of material, okay? And the thing that distinguishes those different phases of material are the underlying symmetry operations that you are allowed to do, which is a fancy way of saying, So basically, if you have a solid, all right, that is in the thermal ground state, then I know that it will have translational symmetry. Or sorry, it will have a broken translational symmetry, which means that I will have atoms that are sitting at specific sites in a crystal lattice, okay? And if I'm standing on one of those sites, I know that if I look, say, 2 angstroms away, I will find another water molecule. And if I look 2 angstroms away in that direction, I will find another water molecule. So it's called a broken symmetry phase, because if I'm sort of standing here or here, right? So say there's an atom here and there's an atom here. These 2 sites look the same. But if I kind of stand vaguely in the middle between them, this looks different, right? So as I walk along my crystal, it's like same, different, same, different, same, different. Everybody got that? That's why it's considered broken symmetry. Okay, this is different than, say, a liquid or a gas, where they're considered to have continuous symmetry. Now, that doesn't mean that you have a continuous swoosh out of atoms in your system, right? Atoms can only occupy little, or molecules rather, can only occupy a space, and if you have one here, then they're going to clunk into one another. So I know that there won't be one that's too close to it. But if I time average over the system, and I ask the question, is there a molecule here? If you wait long enough, yeah, you'll see a molecule here in a liquid. And then if I look, 0.0001 angstroms here, and I say, do you eventually see one here? The answer is yes. So that means that liquids and gas both have continuous symmetry. All right? So phase transitions are about symmetry. Now, are those solid, liquid, and gas the only type of phases that exist in nature? The answer is no. There are lots of phases that you can talk about. So you can talk about a magnetic phase of material. That has a certain symmetry associated with it. You can talk about a superconducting phase of material. That has a certain phase associated with it. For a single component system, though, where everything is non-interacting, it maps down to this solid, liquid, gas discussion. So in general, phase diagrams are very complicated. And in fact, within this solid phase, you're allowed to have more than one type of solid. So have you guys ever heard of like ice 3, ice 4, ice 5, this kind of foolishness? Ah, okay. So this is, you know how we say that ice floats in water, right? So that can be true, but in general, not all ice floats in water. So if you take water, you smush it in a diamond anvil cell, which we previously talked about, you can actually make a different type of ice where that ice will be more dense than water and it will sink. All right, this is like not stable at ambient conditions, but if you had like a ice cream shop in the middle of a planet or something like that, and you were able to make ice, and you took that ice and brought it here to Earth, it would actually sink. And there's experiments where people have done it, and it's hilarious because they like grow an ice cube and then they flip over the thing and then it sinks. I mean, it's all like at the micron scale, but it's sort of fun. Okay. So what was I going to say? Right. So there are those three, but there's also many other phases. What about the snow situation? All right. So if I were a grade 1 teacher, I would go, look over there, and I can just ignore snow. But does anyone know why snow is not on the phase diagram that I'm showing you right now? Say for water. Why is there no snow? What do you mean by constantly changing? Is it a non-equilibrium structure? Absolutely, it's a non-equilibrium structure. Very good. So snow is basically kinetically trapped, okay? So if you were to take a big pile of snow and then wait for a long enough period of time, holding the temperature and pressure constant, what you would find is that the snow would actually turn into ice, all right? Does that make sense? And you can actually expedite this process through applying a bit of pressure to it, right? So if you like smoosh it a little bit, then you get ice at the bottom. So this is where you get things like glaciers from. Or if you add a little bit of heat, you can help it along. But in general, snow is a non-equilibrium phase. So what I am talking about today are equilibrium phase diagrams as opposed to non-equilibrium phase diagrams. The non-equilibrium phase diagrams are even more complicated than the equilibrium one because in general, it matters how you got there, right? So you know that equilibrium phenomenon doesn't care about the history. It only cares about the macroscopic thermodynamic variables, where the non-equilibrium phase diagram matters. Which is why you can get like different kinds of snow. You know how you get like the nice fluffy snow depending on the weather? That process in which snowflakes grow varies in general. So you can get different types of snow. Okay, now, where was I? Right. So what are we talking about here? So we're talking about a simplified system where I have some phase, a liquid, and I want to pull out the piston where I'm going to increase the volume at constant temperature. Okay, so what does that look like on my little phase diagram? So I start off at some particular PT value. So say here. And which way is my, where am I going to go? Down, correct. All right, so I start pulling out the piston, and the pressure in my vessel is going down, right? And at some point, if I do it slowly enough, I'll stay on the equilibrium phase diagram. At some point, I'm going to hit this line. So what happens when I hit that line? Phase transition, good, which you would call what? So the phase is called water vapor, yes, but what's the actual transition called? Nope, I wouldn't call it evaporation. Honey, could you put on the tea, please? Oh, sure, I'll just go put it in the kettle. Boiling, yeah, that's right. Okay, so this is called boiling, right? So as we increase the volume along the isotherm, the pressure will decrease. So we move from top to bottom. So now I have a question. How does the pressure change as a function of volume at fixed T? So the answer is given by something we previously discussed, namely the equation of state of the material. Okay. So previously you have calculated equation of state for specific systems, but you can also just imagine doing a measurement of this guy at as a function of T, V, and F. All right, so qualitatively, it should look something like this, where this points at this thing. All right, so I've got P, V, where importantly this, so these two parts here have different slopes. And note that there's a flat region in here, all right? So suppose that I'm starting up here, all right? And I'm expanding the system, and I'm measuring the pressure inside of the container as a function of volume at constant temperature. So I'm going to get some slope, right? So I expand it by, I don't know, 1%. The pressure drops by 2%. Then another 1% change in volume goes down in 2% until something interesting happens. And the interesting is suddenly I'm able to expand the volume, but the pressure remains constant. Until finally I get to some critical volume where when I keep expanding again, the pressure starts to change again. But now we'll say that it's changing with a slope where it's linear with volume. So these two regions have different slopes. This guy's flat. So initially, and in general, relaxing the volume, constraint results in an expansion in phase one. All right, where phase one is whatever phase that you started off in. In this case, it is the liquid. And for our particular experiment, you determined the initial pressure during what I'm going to call the prime stage. The prime stage is where I remove the air. All right, so now we're going to do a demo because students love demos. And today, as a special feature, there's going to be a real demo. Normally, I just like fake the demos and we just sort of imagine what it would be like if you had a demo. But this will be a real demo, so don't get thrown. All right. Yeah, I dumped over the, why did I dump over the garbage can? See, and you remembered it. That's true. Class set can be sort of dangerous sometimes. Okay, so here we're going to do a demo. So wait for it. Okay, you ready? So this is water. This is a syringe. Everybody ready? So what I'm going to do, I'm putting water in the syringe, and you can see there's a bit of air in here, right? So I'm going to do that thing which they do on, like, you know, movies where there's a drug dealer and they're, anyway, where they like, yeah, that thing, right? And then, hold on. Well, I guess it's not even a drug. Does anyone know why they do that? Yeah, that's right. Exactly. If you're going to die, you want to die from the drugs, not from the air, right? Okay. So here we go. I've never done this before because I'm, you know, not a drug dealer. But okay, there we go. Good, good, good. Okay. So now I have a perfect container of water, right? There's no air inside this thing. And it's at some initial pressure. In this particular case, the pressure is whatever the room is, right? Fine. Okay, so first thing I'm going to do is I'm going to smoosh this. All right, everybody ready for this? Okay, so it's quite difficult to do that, right? So sometimes people will say things like water is incompressible, right? You ever hear that statement? Which is a totally ridiculous statement because water is totally compressible. It's just incompressible by me. Okay. So the reason people make the totally ridiculous statement is because, you know, they haven't actually calculated the equation of state of water, and so they don't realize that it's just a really, really strong slope. All right, you can smoosh water. That's a thing that you can do, and in fact, you could do it with that shock wave that you were showing me at the beginning of class. All right, I guarantee you can smoosh water, and it does cool stuff. We're not going to do that today. Okay, so what I'm going to do today is I'm going to go the other direction. All right, everybody ready for this? This is going to be epic. Okay, so what you have to do is watch here, and then I'll pass this around afterwards, so it's okay if you can't quite see it. So I'm going to close this like this, all right, and then I'm going to expand it like that. All right, plasma curing. What do you see? Bubbling. Okay, so why is it bubbling? So first off, what are those bubbles? Okay, I have an idea. Let's use hands. Yes, read. Is it air being released? Yeah, there's probably a bit of air being released. So let's just repeat the experiment now. Okay, so fine, there's no more air in the water. All right. Yeah, exactly. Which is boiling. You see it? All right, pass it. Okay. So here is my question, though. So where is that flat region that I mentioned? Right? So in this little discussion here, I said, fine, if you were to take the water and smoosh it, right, then you would find that the pressure would go up. And I can't actually smoosh it because the pressure is too big, so I can't push that hard. But I claimed that as you expand it, you get a flat region. So what's the flat region? What would you measure that's flat? Anybody else? Keep talking. While it's blowing what? Right, so let's think this through. I pull it like this, and now what do I have above it? Vacuum. So I have vacuum. Okay, fine. So if I measure the pressure of a vacuum, clearly it's 0. And then what does it do? So it's going to start boiling, right? And to what extent will it boil? Does all of the water instantly boil? No. So how long will it boil? Where equilibrium is what? Exactly. Yes, until the vapor pressure is equal to the pressure on the water. Okay. So let's suppose that I examine this very carefully, and I say, I start like this. So I've pulled it quickly. I have vacuum. And then it will boil off a bit, all right? And as Brady mentioned, it will keep boiling until the pressure in the upper chamber reaches P vapor, all right? So P vapor is this flat pressure that you hit right here, okay? Now what happens if I pull it out a little bit more? All right, so just to be clear, here's my piston, right? Piston and piston. I should make these, hold on. So in each of these successive pictures, right, V1 is less than V2 is less than V3. In each one of these pictures, the volume was a little bit bigger. And so this guy will start to boil off itself, right? And it will do the same thing as before, in that it will keep converting. So you keep going from a phase transition from the liquid phase into the gas phase until the pressure in the upper chamber is equal to the vapor pressure of the liquid, all right? What happens though when I run out of water, right? So the amount, pardon me, what happens when I run out of liquid water, right? Between each one here, here, here. So I'm conserving, obviously, the mass of H2O within the system. But I'm boiling off my water. So what happens once I run out of water? Then where am I on this equation of state diagram? Yes. Exactly. Right? So between V1 and Vn, the pressure that I measure inside of this system is constant, all right? So my vapor pressure. And I've been able to change my volume until eventually I can expand it even more. And here I actually have to start pulling to get it to maintain like that. And the reason that I have to, we'll call this P chamber. The reason that I have to pull like that is why? Why do you have to pull to maintain that pressure on the inside? Because I'm surrounded by air, and the air is at a certain air pressure, right? If I were, out in space, I would have to actually push on the container to maintain it at this low pressure, right? But we're surrounded by 1 atmospheric pressure, so if I want to keep the chamber below that, I have to keep pulling. Okay. So we have discovered a phase boundary between the liquid and solid phase. Okay. Notice that this phase boundary was accompanied by a flat region in the equation of state. Oh, thank you. Okay, actually that's an interesting point. So let's suppose that I was super strong, okay? And I could smush the water. What would happen? Can you compress a liquid into a solid? So flat up, I have a liquid. I can compress it into a solid. Always? Okay. Helium can freeze at high pressure. At ambient conditions, okay, hold on. Helium can turn into a solid at high pressure. At ambient conditions, if you cool liquid, it will form a superfluid, which is not a solid phase. But if you take that same phase and smoosh it, you can form a solid phase of helium. So there does exist solid phases of helium. Now, to be fair, it's not clear what those solid phases are like, and some people think that they're actually like super solid, and there's these crazy experiments that were done like a couple of years ago, but it's like super controversial. But in general, yes, you could form solid helium. So that's an example where, yes, you smush a liquid will form a solid. So that, again, my question. You can or cannot? All right. So everybody take out your imaginary clickers. All right. So we use imaginary clickers. All right. So everyone who thinks that the following, so we're going to do, I'm going to make a statement, and we're going to do the true or false thing. All right, I got to be careful. If you smoosh any liquid at constant temperature, eventually you will get to a solid phase. True? Everybody click away. Or false? Click away. All right, click. All right. Now I put it into the computer. Type. So the reason that I use imaginary clickers is because it occurred to me that no one will ever get it all right or all wrong. And so you basically have to address both questions anyway. It doesn't even matter. Plus they're cheaper. All right. Okay, so we're gonna do a little aside here. Whoosh. So basically this whole question depends on what this little arrow is doing. All right. If you assume that the phase boundary between solid and liquid always is positive, okay, so it always goes up, then that means that no matter where I start in a liquid phase, if I compress at constant temperature, I'll smash into that line, right? And I'll solidify. It turns out though, so just to zoom in on this, right? So, right, I have, if this line goes up forever and is positive, then I have to hit it. It turns out though that there are materials which actually have a turnover in the melting line, and they have a negative slope, okay? And as you go to higher and higher pressure, it's looking more and more like materials will have phase diagrams that look like this. So this is something like solid 1, this is solid 2, this is solid 3, and so on. And where the differences between these solid phases are like how you pack the molecules or the atom in your liquid or in your solid phase, right? So in one of them, maybe they're arranged like a cube, another one it's sort of more of a triangular thing or whatever. And if you were to start here with your liquid and compress, right? Here I'll go into a solid phase. As I keep compressing, actually, I can compress from a solid into a liquid. So if I smoosh on a solid, suddenly it melts. And then I keep smooshing, and then it turns into a different type of solid. And then I smoosh it more, and it turns into a liquid, and back to a solid, and back to a liquid, back to a solid. Whereas if I were to start here on the exact same material and compress, I could do so at some temperature where Tmax is higher than the maximum of all the melt lines for all the different solid phases, right? Now, I mean, eventually you get into like really high pressure and, you know, nuclear fusion happens and you hit sort of like the core of a neutron star, which I guess is a solid phase, but ignoring neutron stars, which I guess in general one shouldn't, but apart from neutron stars for the type of situations that you're talking about, you can conceivably just compress, and stay in the liquid phase before other crazy stuff happens. Like, I mean, eventually it turns into a black hole as well. It probably gets hotter at some point because it would be hard to isothermally compress a black hole. Or is that, I'm long dead. Okay, so everyone who, I don't even remember what the statement was, but everyone who anticipated the turnover in the melt line and the multiple solid phases and the melting through pressurization, you got it right. And everyone who didn't, sadly, you got it wrong. All right. Okay. It feels like it's time for a new page. All materials, if you smoosh them hard enough, eventually will get to the point of something like a neutron star. So I guess if you accept that neutron stars are a thing, which they are, then true is right. But when I posed the question, I hadn't really thought of the neutron star answer, so I was sort of like leaning towards false.
So like ignoring
Exactly. Exactly. Okay. False. Okay. So I feel like it's probably time for everybody to stand up. So we're going to do the stand-up thing. We do a stand-up thing. Hmm? Sadly, that laptop was stolen. I know. I don't want to talk about it. It was sort of emotional. I did name it. Yes. Telemachus is no longer with us. Telemachus, the son of Odysseus. All right, anyway. I will explain it to you later. There's a whole thing, you know, like the Iliad and the Odyssey. Goes on a boat, goes away for 10 years, fights for 10 years, gets lost for 10 years, comes home. I think we need to work on the like other aspects of the curriculum. Write that down. Okay, so what can we say thermodynamically at this point? So note which variables are held constant. T, P, and N. So the thermodynamic potential, we must consider is the Gibbs free energy. All right. You will recall that a fundamental relation is valid for all conditions and describes the single unique equilibrium state of the material. It is useful to think about a fundamental relation which is subject to a constraint of a specific phase. All right, and I'll explain what I mean by that. So normally, when we talked about the Gibbs free energy, or any fundamental relation, I say, right, so Gibbs is a function of T, P, and N. So if I give you some value of T, and some value of P, and some, well, okay, so suppose that I am the knower of all things, all right? Ta-da! I'm gonna waste my knowledge on this, but that's fine. If you ask me for the Gibbs free energy of liquid water, okay, all that you have to do is specify a T, a P, and an N, and I'll give you some number back, right? So you're like, I don't know, T 5,000 Kelvin, pressure 6 GPa, and I guess we'll do it as like eeny, meeny, miny, 3 moles. And then I tell you, all right, so what is this going to be? It's like 7, right? And it's going to be 7, so it's free energy. So it's got to be in units, I guess, of joules. That sounds right. I agree. Yes, it's joules because it's an energy. And I haven't said anything about what state that water was in at the particular time, right? I just gave you back a number. Let's say, though, you said, right, temperature 1,000 Kelvin, pressure 1 gigapascal, and 3 moles. But let's force the system to be ice, okay? I would say, well, if it was ice under those conditions, then the free energy would be 9. And you said, well, what about if it was water? And I'd be like, it could be 7, like a liquid. And then you say, well, what about if it's a vapor? It's 4, all right? So you know that at equilibrium, you'll only choose what? The state that has the lowest Gibbs free energy, right? But in principle, maybe I could like write down or do some crazy experiments or calculations of what the Gibbs free energy of a material would be if I somehow magically held it in that phase, right? So out of equilibrium, and I held it in that phase. I'll show you what I mean. So I can break down the function into 3 parts. So for instance, the Gibbs free energy of H2O, I could say, is the Gibbs when it's a gas, the Gibbs when it's a liquid, and the Gibbs when it's a solid. So I'm just going to store this, 3 different functions, where each is based on the stable region. And we might say, all right, well, how would you actually get these things? What would this look like? And I'll give you a specific example. So suppose that I'm changing a particular parameter x, which could be temperature or pressure, and I'm measuring the Gibbs free energy of the material as I alter this parameter, right? If the system starts off in some phase, we'll call it phase 1. I would collect some data, right? So I'm writing these numbers down, dun, 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 dun. And at some point, I would hit a phase transition, okay? So like the solid liquid or the gas liquid or something like that. And when that happened, it turns out the slope of the curve changes, all right? So this is the Gibbs free energy as I compress it in phase 2. And this is the Gibbs free energy as I compress it in phase 1. But if somehow magically, as I compress the system, I didn't let it turn into phase 2, what would this function look like? Well, it would go off basically with the same slope that it had before, all right? In practice, experimentally, you couldn't measure this, but if I can somehow magically hold the system in a solid phase, when I heat it past the melting point, then I could, measure the Gibbs free energy or calculate the Gibbs free energy in that phase. And by the same token, if I start in phase 2 and I expand the system, or I cool the system or whatever, and I don't let the phase transition occur, then there's actually data for this function out here. Everybody with me? Okay. So this curve is continuous as a function of this parameter x, and this curve is continuous in the parameter x. But they're 2 vastly different curves. And the reason that they're different curves is because, this is for one structure and this is for another structure. Yes, there's a question. Yes. So at this point, G1 of x is equal to G2 of x. All right. But in general, G1 and G2 are not the same. And in the lab, what you would find as you measured is you would follow this line. Okay. So at the phase transition, the molar Gibbs free energy of the two phases are equal. So in your particular case of something like, say, liquid, so the prime here means per mole. At a particular transition temperature, Tt, and a particular pressure of transition, Pt, if I take all the material in the system and I organize it as a liquid, I'll get a certain Gibbs free energy per mole. And if I take all of that material and I organize it as a gas, I will get the same Gibbs free energy per mole. All right. So when you do that experiment, you go like that, and then you wait a couple seconds for the water to boil off, and you get the pressure in the upper chamber to equal the vapor pressure of the liquid. If you were to go in with your Gibbs meter and say, I'm going to grab some water molecules that are floating out in this vapor phase, and I'm going to look, what is the Gibbs free energy of those water molecules per mole, you would get some number. So you'll get 10. And then if you say, right, now I'm going to walk over to the other part of the container, or maybe swim over, I guess, and then you take your Gibbsometer and you measure that water, and you find out what's the Gibbs free energy per mole of the stuff in the liquid, you get the exact same value. So you can have a water molecule sitting in the liquid, or you can have a water molecule sitting in the vapor phase. And at the transition point, those two water molecules that are on either side of the container have the same Gibbs free energy per mole. This is only true at the transition, which means that at equilibrium, I expect water molecules to be able to go from the liquid into the vapor, and the vapor back into the liquid without any change in their Gibbs free energy. Does it make sense? Okay. So, is there a way that I might experience this curve, right? So say I go into Dr. Easton's laboratory and I do the experiment. And I do things slowly and carefully. And I'm smooshing. And I'm measuring the Gibbs free energy. I get these numbers back, right? And so I follow this red curve. Is there a way that I might go up on this dotted curve? Can you do the experiment that you go up on the dotted curve? Ever? Any ideas? So X is just a parameter. So it could be temperature, it could be pressure, it could be volume. Yeah, any parameter. I mean, so it's Gibbs, so it's probably going to be Tp or N. But in general, this argument holds for any thermodynamic potential, and X is one of the variables that you can check. Can I skip over a phase transition? Right? That's my question. So can I, to give you a specific example, can I raise the temperature of water past the boiling point? Or can I cool water below the boiling point? Okay, so what do you have to do? Okay, so let's be careful in how we speak here. So what you said is a true statement. So if you say the boiling temperature of water is 100 degrees Celsius at ambient conditions, I agree with you, okay? And then if you say, well, I want to bring water to a slightly higher temperature, therefore I'm going to raise the atmospheric raise the pressure of the room. So we like double the pressure in the room, I die. But for the sake of science, we've raised the boiling temperature to like 105 degrees Celsius or something like that. There, what you're doing is you're exploring still a different part of the equilibrium phase diagram, right? So if I go back here, yes. Give me a minute and we will raise this point, okay? So The solid liquid transition in water is different than the liquid gas transition in water. So for liquid to the gas transition, water's pretty normal. I mean, water is never normal, but it's close enough to be. I should really never talk about water. So what you were basically arguing, right, is you are saying, let's get this right. Yeah, okay. So at ambient conditions, I need to zoom in on this. So this is my zoom. Whoosh. You're saying ambient conditions are here, right? Heat the system, boil. This is like 100 degrees Celsius, right? And then I increase the pressure, boil at, I don't know, 105 degrees Celsius. This is basically the argument, correct? Okay. So yes, that is a true statement that you can change the temperature at which something boils via altering the pressure. However, you're still at equilibrium the entire time, all right? Because this, if you think about this g of x thing here is an implicit function of p, all right? So I would just get a different shaped curve. So, you know, you could do it at p1, and then you could do, so this is g of p2, and then, you know, you would still get something that looked like this. So you'd still do the same measurement, but you would find that the inflection point had shifted a little bit. So this would be T2, and this would be T1. Does that make sense? So changing the pressure in this way, yeah, you'll get a different boiling temperature, but you still will not have locked on to that upper curve, okay? So good idea, doesn't work. So the trick to this comes in the fact, and I'll say it again, we are talking about equilibrium phase diagrams. So what is the condition for equilibrium? Okay, so for an isolated system, that is a true statement, but in general, we know that that is not true, right? Remember how I told you I lied to you in the course? So in the first part of the course, I say, let's talk about isolated systems. And at equilibrium, subject to any, when you remove all internal constraints, entropy is maximus. Okay, fine. And then I stopped lying. Well, I mean, I'm still lying to you in some ways. But then I stopped lying to you for a while, and I said, well, actually, it depends on how you connect this thing. Remember with the pizza and the beer? Like when my beer gets cold, the entropy is lower in my beer, and it's still at equilibrium. Right? So how do you achieve equilibrium? You only achieve equilibrium if you wait. How long? How long do you have to wait? Like an hour, a day? Not quite forever. For a time scale, which is what? Oh, right. You have to wait for a long time compared to the characteristic relaxation times within a system. Remember? So it's not necessarily an hour. It's not necessarily a day. It depends on the details of the system. So if you look at the relaxation time for like the air in this room, you really don't have to wait that long. If you look at, say, like me and the decomposition process, if I were to die, it would take like a couple days for me to decompose. Are we good on that? Okay. So, as I was saying, we talk a lot about death in this thing. Yeah, so if you do it fast. So basically, if you take the system and you change whatever your external constraint is, like the temperature or the pressure, quickly compared to the relaxation time of your system, you can actually get it to be stuck in that phase. All right? Everybody with me? So that's one way that you can do it. So you push it into the system quickly. So it doesn't have enough time to react. So the typical way that people do this is actually with cooling. All right? If you have a hot material, right? So say that you have silica, glass, and then you put it into really, really cold water, and then it will quench, get stuck, however it was organized. That's one way that you can get something locked in a particular phase. What's another way that you can get locked in a phase? Okay, we haven't talked about it yet, so I'm not expecting an answer. So basically, if you do it gently, all right, which is sort of hokey pokey at this point, I get that. But in order to, this will be difficult to explain in this way. So what I will do is I will tell you the experiment which you should not do when you go home. The experiment that you should not do when you go home, but you should totally watch on YouTube, is you get a glass of water and you put it in the microwave and you let it go, okay? you can bring the temperature of a glass of water above boiling. And if your microwave doesn't like jostle it around and stuff like that, you will actually bring the temperature of the water above boiling. Okay? What happens, do you think, if you were to like tap the water with your finger or like wiggle it? So it would hurt your finger, I'm with you, but what would be particularly bad about this? Ignoring the like horrible burns. It boils explosively. That's right. And when it boils explosively, it lets off energy. Does anyone know where the energy comes from? So imagine that I have liquid water, okay? And I'm adding heat. So I'm walking up this curve. Walk, 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 walk. And then I get to the boiling point, and I keep adding heat, heat. And this heat is boiling the water, boiling the water, boiling the water, boiling the water, until it's all vaporized, and then I go, bup, 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 bup. Suppose that somehow magically I'm locked in the liquid phase, and I stay along this curve. Okay? You will notice that this curve is higher than this curve. So when you whack that cup of water in your microwave and you flash boil, all of the excess energy that you were storing in that phase is suddenly dumped quickly, all right? And you basically get an explosion, which makes for an awesome YouTube video. Horribly dangerous, don't do this, okay? I mean, plus you're also dealing with boiling water, which is sort of dangerous to begin with. We're not gonna watch it now, we're gonna leave it until class. Okay. You would also potentially get this with pierogies. Okay. So, fine, fair enough. So if I follow the equilibrium trajectory, I see this, where I go from one curve to another curve. And at the intersection point, the value of the Gibbs free energy on both sides of the curve is the same, right? I mean, by the way, this sort of little diagram here, I mean, this is the basic idea behind explosives, right? So you prepare a chemical in a particular way that is not at the equilibrium ground state of some set of chemistry, all right? But it's relatively stable. And then you kind of go like that, and then you like that, and you do a kick. And that kick is enough to overcome the activation barrier to go between the two phases, and then it will rapidly go to equilibrium. And as it does it, it goes kaboom, like that. Does that make sense? Okay. Right. So, at the phase boundary, so the Gibbs free energy of both phases are the same. The Gibbs per mole of liquid is the same as the Gibbs per mole of gas. So the question is, what is different? Well, the density. We observe two distinct phases. So where did my demo go? I'm going to do this. Let's say that I increase the volume 10%. if I hold this for a little bit, this will boil until we said the depression in upper chamber is equal to phase depression in the lower. Okay? But then it will stop. And it will stay like this indefinitely at equilibrium. So I will actually be able to maintain, with the air off, because I don't plug my finger. So assume that that's happening. So I will have less water than I had before, more vapor pressure. And the two things at equilibrium will be able to coexist. Okay? This is super important. Certain types of phase transitions allow for two-phase coexistence. Remember that. And then I pull it more, I'll get less liquid. See, look, there's less liquid now. Okay. I have more vapor. And again, I have two-phase coexistence. Then I pull it some more. Boiling. Look at it boil. And now all the water is gone. Okay. And now I'm back to a single phase. Don't write that down. Yeah, that's right. I'm gonna get in trouble for like union things or something like this. All right, so liquid here's my piston. Hold on. So liquid, vapor. Tick, 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 tick. So liquid, gas, liquid, gas. So this is a crucial point. This thing here was not some sort of weird intermediate where the experiment hadn't finished or something, all right? This is stable at equilibrium, right? So phase transitions which exhibit two-phase coexistence are called discontinuous. Phase transitions. Okay. So, first question. Do all phase transitions exhibit two-phase coexistence? No. Okay, good, fine. Next question. We'll get back to that. So the answer is no. Next question. Suppose you are doing an experiment, and during the experiment, you're observing a phase transition from, I don't know, gas to liquid or something like that. And you observe two phases. Does that mean you have a discontinuous transition? Why not? So, if you have a phase transition where at equilibrium you see two phases and it's stable, that's one of the conditions for a discontinuous transition. There's another condition we're going to talk about in a minute. But think about the opposite statement of you're doing an experiment, you're watching a phase transition happen, like something's boiling or whatever, and you observe two phases in your experiment. Does that mean that this is necessarily a discontinuous transition. I didn't say that. Then no. Right, okay? So there are phase transitions which initially look like you have two phases, but it's not stable, all right? And we'll see that. So I want you to remember that. At equilibrium, if it's stable, it's discontinuous. But just because you see two phases doesn't necessarily mean that you have a discontinuous transition, because it depends on the details of your experiment, okay? Okay. So let's think about what's different about these two phases. So I said that one thing that was the same about the two phases is that the Gibbs free energy per mole in the liquid is the same as the Gibbs free energy per mole in the gas. But what's different? The thing that is different is the density. So let's let rho initial equal the initial density of my system, which in this case, I guess, is a liquid. And I'll let rho final equal the density at the end, which in this case is a gas. And now what I want to do is I want to plot, rather than P and T, I want to plot for this expansion experiment, V is a function of P through the transition, right? So before the transition, right, as I expand, as I reduce the pressure on water, the volume goes down. And I know that if I start with a gas, actually, we're going to make this rho. So this is rho. Can you see that? So this is rho, and this is P. So initially, I have high density in the liquid. As I decrease the pressure, the density falls off. So this is the liquid phase. Whereas if I were to start from a gas and compress it, it would have a low density. As I pressurize it, the density would go up until I hit PC. So this is P critical, or P transition, we'll call it. The question is, what happens to the density of my system in this little region here? So naively, you might think that during a phase transition, right? So does everybody agree? So the density here, so this is high, and this is low density, right? Naively, that you might think that as you go through the phase transition from, say, a liquid to a gas, the density of your system just changes continuously from one to the other, right? So you start off with density of like 1 gram per cc, and then it goes 0.9, 0.8, 0.7, blah, 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 until you get to the density of gas, which is like way less than that. But it turns out there is never a region with a density P intermediate in a discontinuous transition. So the material is either a liquid or a gas. What changes is the amount of each. So initially you start off with 100% liquid, 0% gas. And as rho, the average density of your system is changing, all that's changing, so rho intermediate or rho average is equal to, we'll say, some fraction F of rho liquid plus 1 minus F rho gas. So this is another thing that's important about discontinuous transitions. And at this point, and I probably should have started the class this way. So Reed, you had a question. Your question, you said, well, isn't water sort of complicated because you have like a turnover in the melt line and so on? It is the melt line that you were referring to. Yes. And the answer is yes, water is a special case. So typically, rather than talk about water for phase transitions, what people talk about is something that we previously discussed in class, namely a van der Waals fluid. And the reason that they do that is because, so let's about van der Waals fluid. The reason that they do that is simply because the equation of state for a van der Waals fluid is much more straightforward. And I'm going to draw out now in the 2 minutes that remain what will lead us into next class, which is namely the possibility of a different type of transition. So at this point, we've talked about a specific type of transition called a discontinuous transition. I have not said discontinuous in what, I just said discontinuous. And I guess grammatically you might expect that there would be a continuous transition. So I'm going to draw out something that I want you to think about, which is the following. So this is the van der Waals equation of state, which you have already seen. If I take this guy and plot it for different values of t, and I plot p as a function of v, I will get the following curves. So this is one curve. So T1. This is another curve, T2. And if temperature is sufficiently high, I will get a third curve, T3, where the important feature between these two, the difference between these two and this one, is that these ones have this negative region. Okay, so it goes up, then it goes down. Whereas this guy just goes continuously up. So when we start next class, we are going to be dealing with this picture to understand the second class of phase transitions, which are known as continuous ones. And then I will explain what exactly the continuity is in. Okay, so it's my understanding that it is now pierogi time. And well, then we better move the pierogies to my office. All right, and then we will do a pierogi. I'm sure we will find somewhere for a pierogi fest, but pardon me? The science board. Well, I'm still being like recorded and evaluated right now, so I didn't say that we were going to go to the science board. But, okay, good. So remember, your assignments are due, what did I say, tomorrow? By